Welcome, ladies and gentlemen. Let's take a look at our application of differentials for our Bellwork today. So suppose that a cube has side lengths of 5 centimeters. We'll use differentials to approximate the anticipated change in the surface area of the cube, bless you, if its edge length increases by 0.02 centimeters. And so, what are we going to approximate? We're going to approximate the change in the surface area, and that's why it's appropriate to use differentials here. Differentials give us an estimate of the small change that's anticipated, right, in the function value based on a small change in the independent variable value. Firstly, though, we need our equation for surface area. And so thank you, a big shout out to Tyler for providing the visual aid representation with the Rubik's Cube. What formula will we use for surface area, right? What will you use for surface area, Kobe?
6 side length squared.
Cool. So we want to call it S or X? S, I'm down. And we'll call that surface area A is given by 6 times S squared, where S represents the side length of my cube. All right, so what do we need? Well, we need our differentials equation. So in general, I'm thinking that if a function, bless you, if a function y is given by f of x, then we know dy dx equals f prime of x. And by interpreting the dy and dx, right, as separate quantities called differentials, infinitely small changes in y or x, right, like Leibniz did, we could multiply that dx over, treating it as its own quantity, and generate our generalized differential. Dy is given by f prime of x times dx. The key here is that we're going to apply it to our area formula, the surface area formula for our cube, and our f prime of x, the instantaneous rate of change, will be taken at that 5 centimeter side length, and then we'll go ahead and use delta x for my small step over of 0.02 centimeters. So here we go. If a is given by 6s squared, then dA, right, that small change in a must be given by f prime of x, in this case would be a prime of s, would be 2 times 6 is 12, s to the first, and then multiplied by ds, a small step in my s value. How much are we stepping? We're stepping 0.02 centimeters, comma baby, and so we'll go ahead and put that in for 0.02 centimeters. We'll go ahead and plug in my 5 for my current side length, was 5, so 12 times 5 is 60, is that right, 60? Oh, you're looking up. So 60, and that's my anticipated change in the surface area, and so I'm getting 1.2 square centimeters. Is that what you guys are getting, 1.2? Awesome. Raise your hand if you already had that. So who had the 1.2 square centimeters? So some of you are smiling now, some of you are frowning now, and I can't imagine what that relates to, but enough about that. I'm going to go ahead and pause. I'm going to pause. Okay, ladies and gentlemen, let's go ahead and take a look at how we can approximate the value of a definite integral. Remember, from your quick review, you saw you were doing lots of products. A definite integral represents a product between the dependent variable value and the independent variable value, right? This product can represent all kinds of things, like accumulated change over an interval, right? How much oil leaked out of the ruptured tanker. It could be distance traveled, like in your quick review assignment, right? Feet per second times second equals feet, right? And so, in its most basic sense, a definite integral is a product between the dependent variable value, that's the y-axis quantity, and the independent variable quantity, the x-axis quantity. What we're going to do is approximate the value of definite integrals, that is, accumulated change over some interval, using area approximations today. We've got all kinds of tools in our bag from last year. We've got midpoint rule, trapezoidal rule, we've got a left-hand sum, right-hand sum. We're going to point out some key notation differences and then also pay attention to when a particular approximation would be an over versus an under estimate. All right, so on May 7th, 1992, the space shuttle Endeavour was launched on mission STS-49. The purpose of which was to install a new Peregrine kick motor in an Intelsat communications satellite. Do you guys recognize Peregrine and apogee from physics? That's what I'm talking about, right? Has to do with elliptical orbits. motor and Intelsat communication satellites. The table provided by NASA gives the velocity data for the shuttle between liftoff and the jettisoning of the solid rocket booster. We use these data to estimate the height of the Space Shuttle Endeavour above Earth's surface 62 seconds after liftoff. And so I gave you guys a table so that we can attack this. The key is, which approximation are we going to use and why? As I consider the values in my table, right? We're not told to use midpoint rule, or a left-hand sum, or a right-hand sum, right? And so if we're given a choice, we can certainly consider the number of subintervals that we could do here. It looks like our data here, 0, 10, 10, 15, 15, 20. Is our subintervals all of equal length? No, they're not all of equal length. And so we're going to have to break it up and do a separate product, right? A separate product for each subinterval. However, I still think, let's see. We could do a left-hand sum, we could do a right-hand sum, we could do a trapezoidal sum still, but we have to pay attention to our delta x. So what do you guys want to use for this first one? A right hand? Let's use a right hand. And so if we break this up into subintervals, we can gain an approximation, right, for the height above Earth, right, by taking a product of my velocity in feet per second times my time intervals in seconds, and I'd be left with feet above Earth, which is what we're after. We're choosing to do a right hand sum. By choosing this, right, we know that our approximation, it looks like according with this data, strictly increasing, this approximation, right, will likely be on overestimate because we're going to be using the bigger function value in each case. So we're not going to go with t in this one. We're going to go with, what do you guys say, r? So I'll do, so your textbook calls an area approximation with rectangles a RAM, for rectangular area approximation. The first R is going to represent right-hand endpoints are used to generate the height of the rectangle for each of your area calculations. LRAM would be you're using the left endpoint of each subinterval to generate the rectangle height for your rectangular area approximation. So that's not a typo. We'll do RRAM for right rectangular area. Method? Maybe? Method? We'll figure out what that M is. All right, let's do it. So here we go. We've got launch till we begin rollover is 10 seconds. So my first subinterval is, yes, 10 seconds. And 185. Cool. Plus my next subinterval is only 5 seconds. Is that right?
Yeah.
And 319. Plus my next subinterval, 5 again. Excellent. You're sweet. 7. 12.
Yeah.
I'm bad with numbers. 742. And then, oh gosh, 32 to 59 math is hard already for me. 8, 27.
Oh, yeah.
Is that right? 27?
Yeah.
3?
Yep.
And then a lot. 63?
Yep.
Do you want that?
No. We don't want that. Yeah, we do. We're doing right hand sum, aren't we?
But only the 62.
Oh. Ooh, thanks for reading the directions. So 62 seconds. So this is 6 now. So that's where I saw the confused looks. This is RAM 6. Uh-oh.
Good job, Grace. That was. No, but. I guess.
And then you go, and then I ran.
Yeah, Mr. Fritz is still set.
Is it 7?
Oh, we just didn't write the 0 one, 0 seven number? Or we signed
Yeah, we did. Yeah, we did. It's
Zero
time.
times
Oh, we have 6 numbers. I don't know.
We did like
That's six. Never mind.
The launch of the Gannis for you.
All right, so we're down to 1, 2, 3, 4, 5, 6 subintervals of varying length, and our final one is 3, and we're done. All right, let's go to the emulator and get an approximation. You guys have already done this already.
Yep.
And in your emulator and your calculators, you've done it, and we're gonna get a consensus so that you can move on to the next one. And what'd you guys get? Nothing yet? Oh, I can do it.
54,694.
Anybody else get that?
Yeah.
Hey, great.
I type in my.
So an estimate then for this would be, Emily, go ahead and do it one more time, please.
54,694 feet.
Okay. Now, thank you very much. So raise your hand if you got this also, corroboration. Okay, so is this going to be an overestimate or an underestimate, and why? Quietly tell your partner, and then I'm going to have you share with the whole class. So would this be an overestimate or an underestimate for this situation, and why?
You're right. Yeah.
Okay. Enough talk, now we eat. So what do you guys think? Is it going to be an overestimate or an underestimate? Courtney and Marissa?
An overestimate.
An overestimate, and why did you guys think that?
Okay, so the function's always increasing, so if you take the one on the right side, you're gonna be drawing the rectangle like over every time.
Okay, I agree. So the rectangle, right, are going to lie above the curve with my strictly increasing data here. And now, just because you're given a table with increasing things doesn't mean that, right, there aren't values that are higher in between, right? But for this situation where the velocity of the rocket is steadily increasing, then you're always going to be above with my right hand sum. Okay, so what else can we do? Well, I do want to do a left while we're here. So we should do a left approximation as well, and I'm not going to try and format that, but I'll do an LRAM and then compare it so that I can point out a connection between another technique. And so we're going to do rectangular area method. I'm going to go for it.
That was approximation.
It was. But approximation it starts with a different letter than M, so we're working on what that is. We're gonna work on that. So what we do this time, guys. For left, what are we gonna do now? Well, now we are 10 times 0. And we're only at 62. You guys have it, right?
Yep.
You guys decimaled up? Kobe?
31,000.
Raise your hand if you got the same thing. Anybody else there yet? Yes! That's good news. So what I'm going to do now is box that and say, all right, so I know you're interested in OTL time, right? As are we all. But isn't it good that we went ahead and did the left rectangular approximation as well? Because this 54,000 differs significantly from this almost 32,000, yes? And so what would have been a better method than either the left-hand sum in this case or the right-hand sum? Well, that's the trapezoidal method. So the trapezoidal method is the average of a left-hand sum and a right-hand sum. And so we're going to use the trapezoidal method as a means to get a better estimate because it averages my left hand and my right hand automatically for us, so we don't have to go through and do two separate ones and then, right, and then compare or average them. We can do it all at one time, and that's called the trapezoidal rule. So we're going to go ahead and say that our trap will be the average of our left-hand rectangular area method and our right-hand rectangular approximation method. And I'll go ahead and say that's for L gram n plus R gram n. This is for your text here. The average of those two is the trapezoid. And I call that, I made up my new thing, so that's the trap. That's made up. I mean, right now. So the average of the left-hand sum and the right-hand sum is the trapezoidal rule. And you've seen that already with the basic trapezoidal formula. We sum up, right? We sum up the bases and then divide by 2, right? And there's my average right there, and then times the height, and that's the same. Okay. Great, let's take a look at another situation. So the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table. So it looks like our table here has 0.51. So this time our subintervals are, right, of equal length. And our velocity data here is given in feet per second. So feet per second times seconds would give us feet traveled again. All right, so this will work out well. Let's give an estimate for our distance traveled using n equals 6, and LRAM, RRAM, and trapezoids. How do our results compare? And so here we go. LRAM is going to give us that. I can't see both those pages. I try to do it so they fit on the same page for you guys. That's why I added all that information about the Endeavour. Everything's going to use. So it would be on one page. All right, so let's do it. So which one first? LRAM 6. Because my delta x is the same all the time, I can do 1/2 and then just do my sums. And so L versus R. And now the trapezoidal, let's use the formula and then compare and make sure that it is the average of the left hand and the right hand sum. So let's go ahead and do my brand new notation. And we want 1/2 times delta x was 1/2. And it's the single first function value plus double the internal function values. What is going on here? Well, recall that our trapezoidal formula, right, takes the sum of the bases divides by 2, right, gets an average of them, and then multiplies by the height. And so when we compare our trapezoidal formula with our rectangular area approximation formulas, we need our 1/2 in there times my delta x. That's where it's 1/2 times 1/2. The first trapezoid, right, uses the first function value as its primary base, and then its second base, as we move to the right, is used in the first trapezoid, and then again in the second trapezoid. The third base is used, right, or the third function value is used as the right side base of the second trapezoid, and then again as the left side base, and so on and so forth. And so that's why we have 2's on our interior multipliers and then singles on the outside. And what we want to do is make sure that we're getting the average of those two different ways. And so be ready to share your left, your right, and your trapezoidal. Danny, you got your LRAM?
34.7.
Anybody get the 34.7? Corroborate? Great. 1. You have the right?
I have the trap.
I'm going to go right. And who has the right? Kobe?
44.
Anyone else get the 44.8? Cool. And Sid, what did you get for the trap?
I got 42.85.
You get 42.85?
I don't think that's right.
No. Okay.
It's 39.75.
Yeah.
It's fine. I'm trying to do this.
103.
Yeah.
79.5? All right. So, moment of truth. Ready? So whether we use the trapezoidal formula or we average, right, our left hand sum and right hand sum, we see then that the average of the left hand and the right hand sums gives us the same as our trapezoidal, right? But our trapezoidal has it in all single plug and chug into our calculator, and so that would be our preferred way to go. Great. Okay. The first, I meant to put a screen shade on this because I don't want to give anything away. There we go. So the first table gives us speedometer readings from Riley's car as he drives through a school zone in the snow, which is more interesting. As you consider the velocity, right, think about the area approximation as a product. We're doing a product of my dependent variable values with units times my independent variable value units. And so as you look at this table, what units does the speedometer provide? Miles per hour, right? And so when we do our miles per hour multiplied by our seconds, we're not going to cancel out those units in the same way. And so what do we need to do? Well, I took the liberty of converting this to the nearest feet per second. Hey, because we already know we got a lot of calculating digits today with our area approximation. So what I did is let's just focus on the second one, and let's give an upper and a lower and midpoint rule estimate. So we've taken a look, and I tried to streamline this, you guys. We've got our right-hand side, our left-hand side, and our trapezoidal. That may or may not be different than upper and lower, depending upon my function, right? And then midpoint. And so by practicing with these 3 different examples, I think you guys all get set with the different types of approximations. Take a look at my table. Notice how my upper, lower estimate, right, is going to be different than a left-hand or right-hand sum because look at, in this case, the data isn't strictly increasing or strictly decreasing. You see that? So you have to purposely select the greatest function value on each subinterval when doing the upper estimate, as opposed to purposely selecting the least function value on each subinterval when doing the lower. This will guarantee that you've got the absolute upper estimate possible versus absolute lower estimate possible. And then we're going to do a midpoint sum, and that's not a typo either. Right? In order to divide this up and do a midpoint rule, we're not going to go with all 6 subintervals because we don't have any middle data on each subinterval. We need to go and break it up into just 3 rectangles so that we can grab the middle function value from each subinterval. Let's go ahead and see if we can't do the formula here, and then you guys can make sure that the approximations here make sense. So here we go. Our first for upper is going to be 5. Is it 5 in all of them?
Yeah.
Hey, that's going to save time. So the upper grabs the greatest most function value attained. Looks like I'm grabbing the 31. This time I'm grabbing the 35. I'm going to just use this. Since it's 5, I'll save time. So 31, 35, the 43, the 47, the 47 again, and the 46. Everybody pay attention to these last two. You see why this 47 was used twice? It was used to be the greatest function value, right, of the two on 15 to 20, and then again the greatest function value in 2025. Everybody see that? Great. Let's see if this works. So the 25 is the lesser, 31 is the lesser, 35 is the lesser, 43 is the lesser, 46 is the lesser of the two, and lastly 41. So is that good? Awesome. All right, so we got decimals on that. And what did you get for the first one, Danny?
1245.
And that'll be feet. So raise your hand if you have the same for the upper estimate. The upper estimate, okay. And then, what did you get for the lower estimate? You got the lower. Grace?
1,105.
1105? Which of these is better? Well, we don't know necessarily, because this is tabular data and it's not strictly increasing or decreasing. In fact, we see that we've switched from increasing to decreasing along here. We don't know Riley's velocity data in between, in the middle of these 5 seconds. It's conceivable that in between each of these 5 seconds, he slowed down and then sped up, right? As he scans for, I'm just saying, police cruisers, right? And speeds up and then slows down and scans for police cruisers. And then speeds up. I mean, after all, he is in a school zone. Right? Right? Or was it are these both great function values and there's a dip in between? You know what I'm saying? And so this guarantees that the absolute maximum number of feet that he traveled was 1,245 given this data, but we don't have the in-between stuff. We don't have an actual function. All right, let's take a look at M of 3. What? Can we even do a midpoint rule here? Certainly, if we divide this up into 3 subintervals, my first one would span from here to here, right? And we take the middle function value. We take the middle function value and the middle function value. Uh-oh. This isn't going to work if I draw like this, though. So we can go 10, 10, 10, right? 10, 10, 10, and then grab middle, middle, middle. There, that'll work. So let's do that last one. So we've got now delta x, right? My change in time is given by a 10-second subinterval, and we'll grab the middle function value over each in order to give us the height of the rectangle. Again, the key for today, the focus is on the setup. And now let's see how this compares. So what did you get for your mid, Sid?
1,200.
Feet?
Yep.
Good. So it looks like the midpoint approximation, right, gave us a value in between those two, right? In between, but I think it's closer to the 1245. Interesting. Okay. So let's go ahead and close it up. I want you to think about given a positive, strictly decreasing function over an interval. Would my right endpoint rectangular area approximation method be an over or underestimate, and why? Be ready to share? If our function is positive concave up over an interval, would the trapezoidal rule give an over or underestimate, and why? Be ready to share. I'm going to pause. Okay, ladies and gentlemen, go ahead and share your response for number 1. So if we're talking about a positive, strictly decreasing function over an interval, is my right endpoint rectangular area method an over or underestimate and why? And what did you get for that, Grace and Riley?
An underestimate.
An underestimate? Raise your hand if you also had an underestimate. Underestimate? Great. And so why is it going to be an underestimate then?
Because the function values used are the lowest on the interval.
So on each subinterval, my function value used is going to be on the right-hand side. So it looks like the area of the rectangles lie beneath the curve. Awesome. Thank you. I'm just going to say that. The rectangles lie under the curve or beneath the curve. Cool. Given a positive concave up function over an interval, will the trapezoidal rule give an over or underestimate? What do you guys have for that? Vivian? An overestimate? Raise your hand if you over or underestimate. An overestimate, so who else had an overestimate? Overestimate, stop writing, good, okay. Resume. And then why would that be an overestimate? Right? Why would that be an overestimate? Danny?
Because the edge of the trapezoid is always going to be on top of the curve. Above.
What if my function was increasing though? Concave up is not going to matter. Right, I'm always going to be above it. So my trapezoids are always going to lie above. So that concave up, right, ensures, even if I have different length subintervals, then my trapezoids are going to lie above the curve. Thank you, Danny. Good. Alright, so because I wanted to get the running data on the same top-bottom slide, you'll have to write this down on your own or group Snapchat share. So here we go. OTL number 1 is a double-decker because we've got rectangular approximations in 277 and then the trapezoidal approximations come from the 320. You're going to have a nice chunk of time. And so my goal for you not to have too much work outside of class, I'm going to go ahead and stop the recording now and give you guys an opportunity to write that down.